Hi, I'm Dr. Incognito. In this video, we're going to discuss tangent lines. So the first question is, what is a tangent line? And we'll begin with a circle. A circle with a center and a certain radius. You take a point on the circle, and at that point, you can draw a tangent line. What exactly is this line? In the case of a circle, you can say that it is the unique line that goes through the point P and no other point on the circle. That will give you a definition of a tangent line in this case. However, this line has some real significance in relation to the circle, aside from just that one property. And this discussion of tangent lines going through one point and being the only such line that does so doesn't apply to other curves. And we would like to be able to talk about tangent lines to other curves. Let's take a look at a parabola. Let's say that's a parabola. Let's say we have the point P here on the parabola. There's going to be a tangent line. And it is true that the tangent line is going to go through P and no other point on the parabola. But there is another line that also goes through P. You could draw, assuming that my axis of symmetry in the parabola was vertical, then you could draw a vertical line through the point P, which will also touch no other points on the parabola. But this one, the blue one, is not a tangent line. It touches only one point on the parabola. It touches only the point P and no other points, but yet it is not a tangent line. A tangent line has deeper meaning than just touching one point on the curve. That's just in the case of a circle. That description is sufficient. Another example is, let's take a sine curve. Here's a little bit of the sine curve. If you pick a point, say here, then the tangent line looks like this. And clearly, if you extend the tangent line, it's going to go through another point. It's going to go through another point on the curve. So sometimes a tangent line will go through multiple points on a curve. On a circle, the situation is nice and clean. For a circle, you could say that a tangent line through P is the unique line in the plane that goes through P and no other point on the circle. But in general, such a condition is not acceptable. So we need to have another way of thinking of tangent lines if we want to move the concept from circles to other curves. And there are a couple of reasonable ways of looking at tangent lines. First, let's look at it from a physical perspective. Suppose that an object is being whirled around in a circle. Maybe it's a stone on the end of a rope. And then at a certain point, say at the point P, as you're whirling the stone around and it's going around in a circle, you let it go. So if you let it go, it's going to travel on the tangent line. So there's some physical interpretation. Let's say there's the Earth's orbit is an ellipse. Let's pretend that's an ellipse around the sun. And so at a certain point, the Earth is moving around the sun. If the sun were just to be removed instantaneously somehow, then the Earth would continue moving along in a straight line. It would just start flying through outer space in roughly a straight line. There are other objects that have gravity that would affect the Earth, but let's ignore those for the time being and say that it's just the sun that's responsible for our path. Then if you remove the sun instantaneously, the Earth would start traveling in a straight line, and it would that line would be the tangent line to the point P. And of course you could complete the line. Once you have 2 points on the line, you can draw the whole thing. Another way to look at it physically is that let's suppose that this was train tracks, and let's suppose that at the point P the train derails and just continues along straight. Or maybe instead of derails, let's imagine that we want to have a segment of track available for an emergency stopping purpose. Then how would you place that emergency track? You would want to place it at a certain point in such a way that the train would not have to turn at all. It would just be able to go straight onto the track. And so you would place it along the tangent line. So there are these physical interpretations of tangent line. And then there's yet another. If you take a curve and you zoom in on it, if you zoom in on a circle, the further you zoom, the straighter it looks. Kind of like if you're in the middle of the ocean on a calm day, things look flat. Although we know from outer space that the Earth is definitely curved, because you're actually on the Earth, which is very large in comparison to us, it has a zooming effect and it looks flat. So if you zoom in on a curve, the further you zoom, the flatter it looks. So when it looks flat, that means it looks like a line, and that line is the tangent line. If you zoom in on just some random curve at a point, it's not going to look like that line there. It's going to look like the tangent line. Okay, so the zooming in perspective. When you zoom in on this sine curve at the point P, then the line that you're seeing is the one that I've drawn roughly, the tangent line. All right, so there's a conceptual understanding of the tangent line. A tangent line may go through other points on a curve. There may be other lines besides the tangent line which go through just one point on the curve. So we need to be able to think about tangent lines in ways other than a way that we might be familiar with, that is the circle. Okay, now that we understand tangent lines, let's take a look at the mathematical problem of trying to actually find the tangent line. What I mean by that is find the equation of the tangent line. So in general, for lines, if you want to know the equation of a line, if you have a slope and a point on the line, these two determine the line. And the equation of the line would be y minus y0 equals m times x minus x0, the so-called point-slope form of the equation of a line. So we're going to take a curve, and we're going to take a point on the curve, given, and then we're going to want to make the equation of the line. So if we have a point on the curve, then the challenge will be to find the slope of the tangent line. That's the big mathematical challenge. Once we have that slope, then we can combine the point and the slope to actually make the equation of the line. So I'll take an example actually of a parabola. Let's take the parabola y equals x squared. That's the simplest one. And let's take the point to be the point 3, 9. So here is my parabola, let's say. And for argument's sake, let's say that this is the point P here. The proportions are probably a little bit off, but I like these numbers, so let's stick with it. 3, 9 is my point, and so at this point, there is a tangent line. And I would like to know the equation of the tangent line. So according to the point-slope form, I have 3, 9 already given. So the equation of the tangent line looks like y minus 9 equals m times x minus 3. And so the question is, what is m? What is the slope of this line? Now, normally to find the slope of a line, you need a rise and you need a run. Or you need a change in y, that's the rise, and a change in x. Change in y over change in x. If you have 2 points on the line, y2 minus y1, that will be the rise or the change in x, and x2 minus x1. So that's the formula for slope. And the thing about this formula is that it requires 2 points. And we only have 1 point and the concept of a tangent line. So we have a curve, y equals x squared, a point on that curve, and a concept of what it means for a line to be tangent. Now, how do I find the slope of that tangent line without the second point? And the idea is to take a point very close, take a point Q, which is also on the curve y equals x squared, and figure out the slope of the line MPQ, which is what's called a secant line. A secant line connects 2 points on a curve. So the points P and Q are on the curve, and I'm going to connect them with a line. And I'm going to get a slope there. But that's not the tangent line. So that slope is not the slope that I want. But if I make Q close to P, then this slope will be approximately the slope of the tangent line. So what calculus allows us to do is answer the question, what happens as Q moves infinitely close to P? So we move Q closer and closer and closer, infinitely close to P. But we can't actually let Q be P because we need 2 distinct points. We need 2 points in this formula for slope. So 2 distinct points, closer and closer and closer and closer together. And from this thought process, to find the slope of a tangent line, we're going to need the concept of a limit. The concept of a limit is born. So let me do a numerical example. Let me say that the point Q is the point, let's say x is 3.1, and then since y is equal to x squared, that would make y would be 3.1 squared, which, using my calculator, is 9.61. 9.61. So let's look at the slope. These 2 points are pretty close together, much closer than what I've indicated in the diagram. So those points are pretty close together. The slope of the secant line, PQ, will be very close to the slope that we want, which is the slope of the tangent line. So what is MPQ in this case? The change in y is 9.61 minus 9, and the change in x is 3.1 minus 3. That's 0.61 divided by 0.1, and that's 6.1. So the slope of the tangent line is approximately 6.1. In fact, it looks like it's a little less than 6.1, because the slope of the tangent line is a little bit less steep than the slope of the line from P to Q, the slope of the secant line. Let's try another example. Let's move the point Q even closer. Instead of Q is 3.1, let me make Q 3.01. And then the y, let me make the x coordinate of Q 3.01. Then the y coordinate is going to be 3.01 squared, because y is equal to x squared. And that's 9.0601. And then when you figure out the slope of the secant line, these 2 points are very, very close together. The difference in the y's, 9.0601 minus 9, divided by the difference in the x's, 3.01 minus 3. The 9's go away, 0.0601 divided by 0.01, and that's 6.01. The last example, I got 6.1. Here I'm getting 6.01. And that's still a little bit too big because the same picture applies. No matter where I put Q up here, PQ is going to be a little bit too steep. So I'm going to guess that the M we want, what am I going to guess? I got 6.1 for the first trial, then I moved Q a little bit closer, I got 6.01. I'm going to guess 6 because that certainly seems nice. So I'm going to guess 6, but that is technically a guess. Turns out, though, that that is 100% right. So now I'm going to take a moment and show you how we can get that exact answer and do more than just guessing. Because suppose the answer was some crazy number, an irrational number, we would never be able to nail it exactly. Or even if it was just a weird rational number, we might not be able to nail it with just a couple of numerical examples giving us a pattern. So what I'm going to do now is I'm going to take Q, and instead of putting these specific numbers in, I'm just going to call the x-coordinate of Q x. And I'm going to take the y-coordinate of Q, and I'm going to call it x squared. So now what's the slope of the secant line? It is the difference in the x's, the difference in the y's is x squared minus 9, divided by the difference in the x's, which is x minus 3. The difference in the y's, x squared minus 9, divided by the difference in the x's, x minus 3. So that's the general formula for the slope of the secant line. And then to find the slope of the tangent line, what I need to do is I need to let x get closer and closer to 3. In the two examples, I let it be 3.1, and then closer to 3, I let it be 3.01. So I want to let x approach 3. And while x approaches 3, I want to be looking at the fraction x squared minus 9 divided by x minus 3. Now, if you just try to plug in 3, then what's happening is, if you plug in 3, then Q and P are becoming a single point, and your rise and your run are both 0. If you plug 3 in, your rise is 0, your run is 0, and that's no good. 0 divided by 0 is called an indeterminate form. It doesn't tell us anything. So instead, we have to let x get closer and closer to 3. That's what this is symbolizing. We don't let x equal 3, we let x approach 3. This arrow could be read using the word approach. X approaches 3. Now, fortunately, we could do a little bit of algebra to simplify this fraction. If x is approaching 3, then x is not 3. And so we can factor and cancel. X minus 3, first x squared minus 9 factors as x plus 3 times x minus 3. And then on the bottom we have the x minus 3. The x minus 3 is not 0 because x is not 3. X is close to 3 but not 3. So we cancel. And now we can say that the slope of our secant line is simply x plus 3. And clearly, as x gets closer and closer to 3, x plus 3 gets closer and closer to 3 plus 3, which is 6. And that was our guess. So that's pretty good coincidence of information. But this one is technically rigorous. We are guaranteeing here that 6 is the answer. So the slope of this line is 6. The idea, again, is to let Q get closer and closer to P. And in order to move Q, we label its coordinates using a variable. And that way we can move Q by letting the variable move. We let the x approach 3. So the equation of the line then, to finish it out, it's y minus 9 equals 6 times x minus 3. And you could put that in the more familiar form, y equals mx plus b. Y minus 9 equals 6x minus 18, and then add 9, so y is equal to 6x minus 9 is the equation of that line, which seems reasonable. The slope is 6, it's a positive slope, and the y-intercept will be negative 9. Okay, so there's a discussion of tangent lines. Thank you for watching.